Let's continue. So we will be basically using Keras to build our intuition for the feed-forward neural nets we'll be building. So if you look at Francois Cholet's Twitter feed, so we can get an idea of these mine GitHub, and you can see Keras is right next to TensorFlow, and this is just mentions on archive. So both academia and industry are using it. It's not a okay. So we'll build a dense feed-forward shallow network. That's exactly what our goal is. So this is essentially what a dense feed-forward shallow network is. It's shallow because there's only one hidden layer, this blue layer, right? So when you have a lot of these hidden layers, that's basically, it's deep now, right? And instead of having just 4 inputs in our example, I think we'll have 26 inputs. And instead of having 5, we will have 30 nodes in the example below. So we'll still have 1 output, and the problem is still diamonds 1.
So do you know any recommendation for the size of perceptrons given the percentage or the ratio between the size of number of perceptrons and the number of input values? So if you have
when you say number of perceptrons, you mean number of nodes in the hidden layer?
Yeah. So
oh.
Is there a recommendation or something, or it doesn't matter?
Well, you can, in practice, people mess with that as a hyperparameter and do validation. You know.
In the range of always larger than the number of inputs.
Yeah, generally, right? But it depends on the problem. I mean, so I would not, I mean, what I would think, because these recommendations, all of this, in sort of my mathy opinion, is going to be an incredibly dependent function on the problem, the training data. There's a lot of things going on, the optimization routine, your validation, cross-validation scheme. So if you follow all of that, yes, this will work. But in general, you guys know enough to roll your own sleeves up, and you know the machinery, you know cross-validation. So you just have to, anything that you don't know. In fact, I've done a lot of work on feed-forward neural networks, feedback ones as well, with feedbacks with the student where we're trying to control these, gas plants. So there's so many recommendations, there's huge literature review, and there's all these architectures, architectures meaning the configurations of nodes, blah, blah, blah. So in the end, I think Hamid just exhaustively went through, I don't know, so many combinations, like hundreds of them. And he was just using a MATLAB toolkit and just ran for months, basically, and empirically found the best ones, right? And they were quite good because, he basically found the best one empirically. Yeah, so it's going to depend heavily on the problem and the data set as well you're using for the training. This is quite good. I just briefly looked at it because I'm not like a deep learning guy or anything. So, but yeah, it's quite a quick way we can look at, okay, if you want to get into convolutional neural nets, which we'll do in a bit, you can quickly look at what are the main methods and RNNs. Hopefully we can get there and find out what the main methods are. So yeah, so this is quite helpful. So let's leave that guy. Okay, so this is the game. So we're going to import the sequential and dense. What are these called? Packages in Python? What are these called? Libraries. Modules. Because remember they're package in Scala. Anyway, doesn't matter. Whatever. Tighten those strings. So then model. So what we're basically saying here is our model is going to be, a sequential type, right? So in C++, this would be a default constructor. I don't know what the Python thing is for it. And then we're going to now add layer at a time, right? So here, the first layer we're going to add is dense. Dense is the dense vector, so it's not a sparse vector. And it has 30 units, right? And then, but this is the hidden layer already, and it has input dimension 26, so that's what's going to come in, okay? Because remember, we had 26 features in this example, and then we're going to have because of the one-hot encoding, all those discrete things blew up, right, in the diamonds. And then we're going to have this kernel initializer to normal. So this is how we're going to initialize the weights for the stochastic gradient descent we'll be doing for optimization down the road, okay? That's the kernel initializer. And then our activation function is going to be linear. So how these things are going to be combined when it gets out of the node, that's going to be a linear.
So in this case, the output is a real number. No?
Yes, right, because we're still interested in regression, right? Yeah, so we're gonna basically code the price prediction problem. Yeah. Pretty well, I don't know today, but quite soon we'll do what is that called? Classification. Sorry. Okay. Yeah.
I can't run it. It says no module find clear stuff model. Do we need to import some library or?
Oh yeah, you have to import some stuff. Right. I thought. Yeah. So can I run through this and then I'll tell you guys what to import later because there was a big pack I forgot to. Yeah. So let me just quickly run through this. Okay. Here is the. So yeah, when you run through this, it's so we again set the I'll tell you a little bit about what this Atom is. So this is a particular kind of optimizer. We set up the loss function, and this model.compile basically compiles the the actual model way under the hood. And now I have I'm going to call my fit, and whatever the fit returns, I'm going to put it in this history. And for fit, I need the training data, my training response, and epochs is the number of times the optimization routine goes through the data. And then my batch size is the size of the batch of the stochastic gradient descent. Remember, this generalizes to very large data sets because we cannot find, we cannot fit to all the data. So we only look at random blocks, right? And here are the size of the blocks. So you only look at 200 training sets at a time and another 200 at random for each step of the gradient descent. And then our validation split is 0.1, so we will hold out 10% of the data and use that to decide when to stop overfitting. And finally, we get some scores, and this is how mine should work, I think. Yeah, so you need a bunch of libraries. Okay, so I have only done 10 epochs, so it stops quickly, and as you can see, the mean square error is horrible. It's really, really big. Okay. Yeah, so it's $3,795, dollars so far. So if I do summary, I get layer specific summary. So so this is my shape. I have 30 nodes in the first hidden layer, and there are 810 parameters. I mean, this is kind of crazy, right? So what is, so you guys see how the 810 are there? So you really want to understand this properly, slowly.
The number of inputs multiplied by the number of nodes, and then multiply the number of nodes by 1.
Yeah, I think you got it.
And
Well, okay, so let's just draw pictures, right? So I always get this wrong every time, so I actually wrote down the answer just because I don't get confused. So you see, you have something like, 26, the one hot encoded numbers and everything with diamond, caret, whatever comes in, right? Now we have 30 of whatever these things, right? This is what this hidden layer, whatever, right? So it's 30 of them. Now what's happening from each one, right? So you have this thing goes here, this goes here, and so on, right? And so these are the W's, right? 2, 3. So there's 26 W's. For this guy. And then we multiply that by 30 because for each of these nodes, we have these 26 W's that are distinct, right? Because this guy is going to have his, right, own W, and so on. And then remember there's that 1. So we have the fixed 1 thing, the intercept thing that comes into everywhere. So that's basically why you have 26 times 30 plus 30, right? Okay.
you have weights again, right?
Yeah. So the next layer you're talking about the next layer already? Or? Yeah.
From this layer to the output, you have weights as well.
Well, okay. So that's the dense 2. Dense underscore 2, right? That has 31 parameters. So that has only, remember, we only one node in the next layer, right? When we added in the sequence. So yeah. So there should be 30 and one more from this one, I think. Right? So that makes sense. Huh? Because it's remember that's the definition of the perceptron, right? Yeah. So 31. Okay, so 31 plus 810 is 841. So we're trying to fit 841 parameters to explain a regression with 26, we call them covariates, 26, predictors or whatever, yeah, regressors. Yes. So I mean, it's yeah, that's the structure. Okay.
Behind this process, there is some optimization.
Oh yeah, that's what we're going to get to.
Descent gradient.
Yes, it's stochastic gradient descent. That's it. That's all I've seen. I mean, and various modifications of that idea. And we are using one of the best recommended ones called Adam. We'll see that in a second. Yeah. Yeah, that's...
What do you think is this interval techniques? Is it applicable?
I don't know, man. These are very high dimensions, right?
Yeah.
So Alex done this, in fact, a lot of his work it was exactly what TensorFlow did after him. I mean, I'm sure other people have done it too. So he was doing all this graph processing on intervals and stuff like this, right? And he's doing forward and backward propagations, all of that with intervals. But that's why I met him one day at a party, and he said, "Yeah, Google beat me," or something. So I never talked to him. Right? Okay, so let's whatever you do, you have to beat the best algorithms out there if you work in industry. So we should figure out what they do, right? What is everyone raving about this? Okay, this is just stuff I've already told you, and Okay, so now let's just look at the standard deviation of the root mean square error. So this kind of tells us, okay, the standard deviation of my response. So if you look at the plot of the error, so and remember, guys, if you have the right imports, you can always use Python in Databricks to plot. So people were complaining about not being able to plot, but we've seen this, right? All you have to do in a Scala is do a %py. So anyway, this is training and validation. So we're noticing that the training error will, of course, keep decreasing if the optimization routine improves better and better. But then the held out data we can use to, you know, decide when to stop. Okay, so this thing will take a while. So the main point of this this particular it's just putting everything together. So we read the file, drop the stuff, and get the dummies and shape it the right way. So it's exactly what we did cell by cell, all stuck together. But, so now we're going to have again 30 hidden and 1 that's coming out. And this is exactly mimicking linear activation. And let's see how well this does. And if you do this after a while, you're not going to get a huge, it's pretty close to linear regression, but so the main idea is that when you have a shallow feed-forward neural network with the linear activation function, we can basically get quite close to the mean square error of linear regression. Okay, but it's a lot of work, like 2 minutes compared to like almost no time, right? But we're doing quite a lot of things. We're using a very generic technique of optimization, and so the same architecture can be extended using. So this is something we've seen before. This is just Adam's slides on how gradient descent works. So you know this already, right? So we're trying to optimize fit, and but instead of looking at the gradient of all of the data points, we just do it in steps, right? And these are standard problems with local optimization, right? If your jump size is too big or learning rate, then you can kind of jump around. If the function is more complex, then you can get stuck in local optima, all of the same stuff. So the way we deal with big data is to stochastic gradient descent. We've done this before, right? When did we use stochastic gradient descent before?
Was it with the power plants?
Yeah, power plants, I believe so. I mean, I think a lot of the optimization under the hood is stochastic gradient descent. Yeah. I have to do a grep on all the content myself to find out where it is now, but it doesn't matter. Okay, so, but with stochastic gradient descent, what you need is the derivatives, right, of your optimal objective function. So we need to basically do these calculations cleverly, right? And especially for neural networks, because these are very high dimensional parameter spaces. So this is where the idea of backpropagation comes from. And the other point was, if you ask what is this Adam thing, it's a particular variant of stochastic gradient descent which keeps track of the momentum of your optimizer. And I haven't read exactly what this atom thing is. I really haven't had the time to read it, but it's some recommended variant of stochastic gradient descent. Okay. So anyway, and I don't worry too much because from my point of view, like a lot of this is heuristic because it's local. Okay, so you need to play around, change the seeds, and all sorts of things. But, yep, you have a question.
This sequential model,
Yeah.
when you do this validation split, it already performs cross-validation by changing parameters in some way?
Yeah, because you specify like 10% you hold out, right? Yeah, so it holds this out. Because because you need to also like not overfit, right? You need to somehow know when to stop. So, you need some way of deciding this, right? So you can also look at how your current fitted model does on the held out data, and okay, so back propagation. So this is a very basic idea in finding the gradients in a neural network. So this picture is a bit messed up because in the usual orientation, this is sort of a mirror image. This should be on the left because this is the input. Okay, it's just flipped around. So you can flip it back in your head. So this is the input layer and this is the output layer, right? So yeah, so when we use stochastic gradient descent, we are sort of mainly using it as a way of circumventing having to compute the gradient at every example, right? So that's why we take blocks, batches at a time, randomly. But with deeper network, these are the two main challenges we have to overcome. First of all, the error is computed from the final layer, right? So the gradient of the error doesn't tell us immediately about the problems with other layer weights, right? So you cannot just, because it's such a high dimensional parameter space, you can't just do some Gaussian kernels for initial weights and hope to end up somewhere. So you need to take advantage of the architecture of these arithmetic operations that are there already, right? In terms of finding your gradients in a clever way, reaching the right answer. Okay, so yeah, as you noticed, the tiny diamond model already has over 1,000 weights, and bigger models will get even more complex. So, and of course, all of this is done in like non-rigorous floating point arithmetic. So there's like issues with underflow and overflow models. So the big insight that came with back propagation is to iteratively calculate these errors, right? And the main idea is to do it one layer at a time by starting from the other end, from the output. Okay, and that's why it's called back propagation, because you're starting from the, normally this will be flipped the other way around, and you'll see this is the output. So yeah. So what are we going to do? What is the main steps? So we receive a new observation X and the target Y star, okay? So which is our output. So in the feed forwards process, what we do, we're now going this way. This is the normal way, input output. So for each unit in this node, Gj, in each layer, so let's just take this without loss of generality as one of the layers 1 through L. We first compute Gj based on the units Fk from the previous layer, right? So, there's all these Fi's that are coming from the previous layer, and the Fi's multiplied by the weights give us the intercept term, and the activation function give us the Gj, right? So This is just how we define the model going forward. Now we get some prediction y. So we do this for every node, like usual, going forward. Now we have the prediction y that comes out of these specific values taken by the parameters. And then we have the actual label we want to tighten against. So we define this to be the error. And look, this is all numeric. Now what we want is some way of back propagating this error such that for each unit Gj now, on each layer, we do these two things, right? So we want to compute the error on Gj, right? So what does that mean? That's just the Gjth partial derivative of this error, right? Now the Gjth partial derivative, or so what? Okay, so in English, this means like should Gj be higher or lower from the optimization point of view, right? To decrease the error, right? That's what this tells us. But whether Gj should be higher or lower to improve my fit is going to depend on on this term, right? So we have to basically find out what is the derivative, okay, of hi where Gj is going to be affected from, right? So how hi will change as Gj changes, right? And I don't know. This is just chain rule in calculus, right? I can't explain this in English. Okay. So anyway, it's just chain rule, right? I don't know. Adam did a better job than me. Okay, so I mean that's the key, right? So you back propagate it one unit at a time, and so this way you can really help the this is the magical part, right? Your current weights are predicting y. The value is y star, right? And you want to try to just reduce that distance that you want to do. So you want to really know what should be changed immediately that affects this little number from becoming bigger versus smaller, right? That's all it is. So you only have to look at the next place and make suggestions. So this architecture is beautiful in a way because each layer only learns from the previous layer, right? So this is what you're taking advantage of when propagating the derivatives back as well. And you use that information in the optimization. So, and this is the weights. The weights get updated like this as well. Okay, so this is all Adam's slides. Okay, so we've come up with a very slow way to perform linear regression in the end, right? All of this, but it's just to put our teeth again on the same apple we've been chewing, right? Now the magic happens, right? So now if you add non-linearity, instead of this activation function being linear, that's this last layer, right? Instead of that part being linear, what if we actually make it non-linear? Then you have universal approximation. So you can start fitting very complex functions, right? Including like, is this person smiling or angry, maybe? So here is the basic nonlinear function we will use. So instead of just a line, we're going to use this logistic function. We still have our dot products as before, and we add the bias, the term as before. But now instead of a linear response, a linear activation, we're going to use this guy. So this guy is going to be between 0 and 1, and this is the exact thing used in logistic regression as well, right? Sigmoidal. Okay. Yeah. So where does the signal go? So this is sort of from these neurons. In a regression problem like the diamonds dataset, the activations from the hidden layer can feed into the single output neuron. It's exactly the problem now, with a simple linear activation representing the final output of our calculation. So, but then if we want classification, then we need to choose from, in this case, in the MNIST example, we need to choose from 10 classes. In that case, we can feed the outputs from these hidden neurons forward into a final layer of 10 neurons and compare those final neurons' activation levels. See? Because you'll have just 10 neurons, and each of them will have an activation function in the end, like this, and see if it's turned on or off. So we can train the machine, the network, so that these 10 last nodes, will have some numbers between 0 and 1, and we basically pick the highest one, for example, as the digit that's recognized. Okay. Now here is my so here is this code. So what are we going to do? This is the only change we made. We changed the activation to sigmoid, and then remember, this is still linear because we're still performing linear regression. What we've done is change the activation function in the hidden layer, right? Where's the guy? This one, right? So okay, and then if you do this, you're going to get similar results, and the problem is it's going to take very, very, very long time to converge, because there's a lot of parameters, and when you make the internal layers have nonlinear activation functions, the computational complexity is too slow, and so people almost gave up. Basically, they're like, okay, this is this is terrible. It's great. It's a universal approximation. We can mimic what's the architecture in the brain, blah blah blah. But it really became too slow. So what was needed to make this work better is a much simpler gradient computation. Okay, it means we wanted to be able to do it quite fast, and then it needed to be less prone to so-called saturation, which means the condition where the neuron or each node ends up way off in the 0 or the 1 territory with these nonlinear things. So it sort of goes into these extremes, and then thereby it can't easily learn anything too new. It sort of gets stuck. And then the last thing is we want to make sure that the gradients are kept big enough, right? So this is mainly for avoiding the large, flat, near zero gradient areas of the sigmoid. So the magic kind of happened with ReLUs, or rectified linear units. So this is, this is just the straight line, except now it has a hockey stick, right? This was the original problem back. But it's magic, right? So because see, now you can find the slope really fast, right? What is the slope to the right of 0? It's some number, right? It's just constant. That's nice. What's the slope to the left of 0? That's 0. That's really nice. Well, at 0, it's not defined, right? That's okay. And this basically did quite a lot of the magic. Okay.
So this function from the right, from sort of approximation of the sigmoid function.
This is an approximation of the sigmoid? You guess so. Yeah, I guess you can kind of think like that. Of course, it's not a great one. But the main point is that this...
The gradient we know.
Yeah, exactly, right. Because remember, if it didn't, because the right half is just the usual linear. So this is just a rectified linear unit because it's just translated with fixed 0. So this satisfied all these problems. So people did this and find out, like, why is this slow? What do we need? So kind of, and this is kind of, okay, it's the simplest. Okay, but there's more than this coming up. But
What's happening with the function after 1? Is it undefined or?
no, it just keeps going.
Oh,
Oh, and actually, wait. Yeah, I think so. Right.
the activation can be more than 1? I thought the activation was.
Well, it depends,
But
I
you
guess.
take, but already when you take from above a value, you consider it directly 1, right?
I believe it's just a linear thing, and I mean, you can do other things to it, right? If it's,
I would expect it to look like this, right?
I don't think so.
Okay.
I'm only going by like a whole bunch of videos. I think the only I know for sure. Okay, I'm quite sure that the only point the derivative is undefined is at 0, so it should be just a linear. Because otherwise they should call like doubly rectified linear unit. That should be another paper, right? I actually don't know, man. Let's quickly. I just want to get to the end of this and then we'll continue. So then go change your hidden layer. Oh yeah, this is your homework. Yes, go ahead and do this. Go change your hidden layer activation from sigmoid to ReLU. Okay. And yeah, so let's see what happens basically. Yeah. And that's here. So, and what should happen is this. You should be able to, get very good RMSEs right away and fast, okay? So now we have nonlinear activations, very fast optimizations, and much nicer results compared to straight-on linear regression, okay? So same theory, different activation, huge difference. And now comes, because this is about deep learning, so we have 7 more minutes, right? So let's get into multi-layer networks. So we don't just have one hidden layer, we have many more. And that's basically allows us quite a lot of flexibility and freedom in attacking more complex problems.
So it's up to us to choose this number of hidden.
Yeah, exactly. In fact, I don't know if NIPS is still like this, the Neural Information Processing Society, NIPS. It's very famous machine learning society. It's
Isn't it right now?
Huh?
Isn't it right now?
Oh, are they happening? Yeah, I don't know. I don't go to that community. But anyway, they are all about deep learning for at least the last couple of years. So anyway, and a lot of papers are exactly this. They come up with very creative ways of engineering the architecture to solve problems. I think it's capsule networks? Are they the new big thing in deep learning the last few months? Let's see. So this is not here, right? Capsule deep learning, capsule or something. Yeah, capsule networks, understanding intense capsule. It's quite good. I saw this. It's actually quite good because it's an improvement on convolutional neural nets, which we will see. And I don't know if the libraries yet for this. But people know this. This is this guy, Jeff Hinton, that everyone talks about because poor academic, a lot of people forgot about for a long time, and then boom, it's like you know him or
Yeah. He's from Toronto.
Yeah, right. Yeah. So anyway, you can. Yeah, this is the idea. Well, okay. Let's go here before we. Yeah. Let's do this later. First, you need to do convolutional neural nets before understanding why this is better, right? Okay, where are we here? Yeah. So what we want to basically do is add more layers, right? And I already told you each layer is learning from the previous layers. So this is essentially the picture. This is the shallow or non-deep feed-forward neural network that we just did for regression, and with only one node out here. And this is just the deep neural network. Okay. So people had this idea a long time ago, but the only problem was it was a numerical problem, right? They couldn't do the optimization cleverly, and all sorts of and those got solved. So now your task in the next 4 minutes is to add a layer to your Keras network, perhaps add another 20 neurons. Remember, we had to add 30 blah blah stuff there. Maybe copy that block and put it there. You can do this at home once I send you the right imports, and see how the training goes. And there is also a solution notebook. Don't look at it. And this is Adam's notes. So he's getting an RMSE much smaller than 1,000 by epoch 35 already, right? So it's quite fast compared to the other one. So this is essentially the big news, right? So now you're suddenly able to explain the price difference by $500, right? So that makes a big deal, right? You can predict. So you can sell the right diamond to, I don't know. I mean, you can set the right price, at least based on market prices and features you've extracted. Yeah, I think that should be.
Does it work for non-linear regressions as well?
Yeah, I mean, non-linear. Yeah. I mean, you know what? Well, now we're already not in the linear regression terrain anymore. We've added already another layer. Something is going on, right? There's a new layer is learning from the previous layer. I mean, it's just a whole lot of arithmetic operations. I don't know how to interpret it. For images, it's a lot more natural to interpret it because we can actually see them as images again, or weird image-like things, right? But it's hard to interpret what these numbers mean. But definitely, we've increased the model complexity by adding another layer with 20 more states, and then we overcame well, we know that nonlinear activations are better. Because, you know, you're not just doing hyperplane splits, right? Remember what's going on under the hood is, you know, the first set of dot products with this multiplication by 1 is a hyperplane, right? So you know, and then, so what did the hyperplane do? The hyperplane does the separation of the xi's into, say, zeros and ones, right? Now, that was the original example, but instead of just zeros and ones, now this other thing is giving us some kind of nonlinear function, right? You know, instead of just this jump function, it's something nonlinear. So, but then we have, that's for every node level, right? So what's kind of going on is, you know, you have these nonlinear transformations, you know, usually in 0, 1, or even the real line in general, because ReLU is on the real stuff line. That's happening at every one of these nodes. So it's like hyperplane splits with these nonlinear maps, right? So it's a very general class of arithmetic. So that's what's driving the yeah, and for specific problems we can get insights, and there are people who are very good at understanding. And this thing I just told you, this medium. Yeah. By the way, I don't read academic journals so much anymore, except math stuff, right? This is really amazing. Back channel medium, like it's better than Wikipedia nowadays. So anyway, I will, of course, you know, for pure maths and more, only very few people understand those things. You have to read academic journals. Yeah.
In this first triadic neural network,
yeah,
we're supposed to, the activation function should be linear, or should we already use this?
No, you want to basically use a nonlinear activation function, and you're trying to add an extra layer, right? So you're following the ReLU thing we know works, but instead of, you know, in this one we just have okay, we just did this change, right? And we did this add dense 30, and basically kind of copy this line and try add dense 20 or whatever. And if you're really desperate, you look at this solution here, but you know. Anyway, I will give you guys instructions on this. The other thing that's outstanding is we have Mahmoud has a recommendation of how to fork and make pull requests of your projects, so we can all be on the same page. Okay, so that when you're writing your project and I want you to contribute to this repo, so I don't want to copy paste and push it as myself, because that's kind of defeats the whole point. So, you know, how many of you have already forked this repository, the GitHub repo for the page? So, okay. So if you fork the whole thing, I think it's it's 0.5 gigs, I think. If you
No, I didn't fork the whole thing. I forked.
Yeah. So I was going to do that. So because some of you already have forked, because I see you in the fork. You know, no, someone.
I forked it, but I didn't download it to my machine. I downloaded only the Git.
Right. So do you know what? Yeah. So I'll give you some instructions on exactly the steps you need to do. But there is a break, like you need to have at least a quarter gig, 250 MB, because just my .git file is that big, so I have no way around it. But there's a sparse checkout you can do, but you can delete it when you're done with me. So the steps on how to you guys already know, right? How to fork and make a pull request, and so you can just make a pull request of your DBC archive of your thing. You can just put it there. So you can always export as DBC archive, and I'll tell you which directory to put it in, and then make a pull request so I can see what you're doing. You two back there, don't do it, because you're working with sensitive data. Will be in someone's jail, so don't just ignore it, right? Because you know what I mean. Like we have a lot of sensitive Twitter data. We can't just. So it doesn't apply to you, and you also have access to a different shard anyway. Okay.
Which folder was it?
So it's just here. So let's see. Go here. Star. So I haven't exactly found a place yet, but it'll be in this DBC archives where you guys get 2017.
Okay.
So I don't quite know whether it'll be in parts or, yeah, probably parts. This is where, you know, so I want to put a new folder in here. Yeah, I'll make a new folder, so like student projects or something, and then you can dump it in there.
And then we're putting our projects in there.
Yeah, as a .dbc file, and I think when you make a pull request, I can accept it and see it. It'll be some binary thing, and then I will just open it and see it for now. Because at the end of the day, your project will be one or a few Databricks notebooks that we'll put, and then Tilo and Dan's Haskell library will turn that into a Git book automatically as your own chapter. That's kind of the plan. Okay, there.
The other paper